Hopefully this is recording properly. I think I narrowed the screen. Oh, yep, I think it is. So that's good. So we went over the chapter 27 conceptual questions in class. I'm not going to do that very much, but I wanted to just show those answers, so they'll be available as a PDF also. The idea is that if you have positive charge inside an enclosed surface, you have positive flux, arrows of the field pointing out. Negative charge enclosed, you have negative arrows, or you have arrows pointing in, you have a negative flux. And if you have the same number of arrows going out as coming in, there's no net charge enclosed, and so no electric flux. Hopefully I don't confuse magnetic and electric flux. We'll talk about magnetic flux later in the semester. So here, flux just depends on that amount of charge enclosed. It doesn't matter if the charges are outside. This was kind of a neat one, I thought. So just depending on which charges are enclosed affects what flux you have. This one, we would think about this, even though it said it was a balloon, we can think about this like a conductor because all the charges were uniformly spread on the outside. So the only location in space where the flux would change would be point 2, because initially it's outside the surface, then later on it's inside the surface, so the flux decreases to 0, or the field strength decreases to 0, pardon me. In 8 and 9, these deal with the statements that were listed. For problems, the first problems shouldn't have been too difficult either. I think we actually did, it's problem, not question, problem in class. So I'm going to try to highlight that, change the color, bold. In the background, we're going to make sort of like a light gray. Sure, something like that. So it really should be problem 6 here. And then problem 17 down here. Well, I tell you what, life is difficult for me. Anyhow, okay, never mind. I am going to mind. There we go. I'm going to change that back to non-colored font. Ha! All right. Moving along. If I have something like this, the flux is just dependent on what's enclosed again. So I have no net flux here, plus 2Q over vacuum permittivity here, plus Q here, and plus 3Q here. Problem 24 was a little bit more mathy. It says the electric field strength just above a face of a copper penny, 2,000 newtons per coulomb. What's the surface charge density? So surface charge density is charge per unit area. So we look at that. And so that would equal electric, since electric field strength is equal to charge over area over vacuum permittivity, we can really set those equal. Charge is equal to charge density times area, so we substitute that in for charge over here. The area cancels out, which is interesting, and if you notice, the electric field strength only depends on the charge density. So that's kind of cool. And I ended up getting, and this is actually the same formula that's listed earlier in the chapter for a surface. 1.8 times 10 to the negative 8th coulombs per square meter. For problem 28, this is basically saying what's the net electric flux through the closed surface. Well, the closed surface is in purple over here, so that's just plus Q over vacuum permittivity. That was easy. For problem 36, it gave you a function for electric field strength, and it is 5,000 R squared times R hat, meaning pointing out from the center. So that is a unit vector. So all I have to do to find out if we've got a 0.2 meter radius sphere, plug that in, 200 newtons per coulomb R squared, or R hats, meaning pointing out from the center. So if we know the area of a sphere is 4 pi R squared, that's our area. Electric field times area gives us our electric flux, which is about 100 to 101 newton meters squared per coulomb. Part C, for number 36, is asking how much charge is inside the 40 centimeters diameter spherical surface. So again, that's 20 centimeter radius or 0.2 meter radius. So again, I'm just going to rearrange that. E times A times epsilon sub naught, which is vacuum permittivity, gives us that many coulombs are enclosed. So there's a lot of ways you can manipulate Gauss's law. Problem 37 is saying a neutral conductor contains a hollow cavity, which there's a plus 100 nanocoulomb point charge. Charged rod then transfers negative 50 nanocoulombs to the conductor, afterward which the charge on the inner wall of the cavity wall and the exterior surface of the conductor. So I answered this a little more detail. So I drew a picture because it was a little hard to visualize. So you've got this point charge here of plus 100 nanocoulombs. You've got this conductor, which was initially neutral, but then gets a negative 50 nanocoulomb charge. So in this region here, the flux would be based on that plus 100 nanocoulombs. In this region, which is in between the inner and outer surface of the conductor, we know that by definition, the electric field has to be 0, therefore the electric flux has to be 0, therefore the net charge enclosed has to be 0. So the inner wall of the conductor would have to have a charge of negative 100 nanocoulombs. The outer surface of the conductor would have plus 50 nanocoulombs because it has overall a net negative 50 nanocoulomb charge. The inner wall, the cavity wall, I guess you would say plus 100 nanocoulombs. That means right here, I think they really meant was the inner wall of the conductor, and that's negative 100. For problem 45, it says this is plastic, but the plus charge is uniformly spread on the outer surface, so it's behaving like a conductor. So the electric field inside is going to be 0 newtons per coulomb, so there's no charge enclosed. From the outside, again, we'll look at the general formula for electric flux. 4 pi r squared over the charge enclosed over epsilon sub naught, and we get something like this. And once again, that is the electric field for a point charge. I wouldn't put this down because it's not well, I guess you could put either one of these down. That's the same for an electric field from a point charge or on the outside of a sphere. Looking at this is 46, and I think I said it was by far the toughest problem. I hope you gave it a shot. So it's a uniformly charged ball of radius A and charge negative Q is at the center of a hollow metal shell with an inner radius B and an outer radius C. The hollow sphere has a charge of plus 2Q. Determine the electric field strength in the 4 regions. R is less than or equal to A, R is between A and B, R is between B and C, and R is greater than C. So easiest ones are on the outside. So I'm going to start working on the inside because I'm just taking the difficult one first. So the reason that this is tough is it said it was uniformly spread, meaning the amount of charge is everywhere in that plastic and not moving. And so the density, and I believe this is, I forget what Greek symbol that is. Not lowercase delta, but anyhow. It's a symbol for density here, charge density. And that's equal to negative Q over 4/3 pi A cubed. So A is the complete radius where the charge is enclosed. So charge over volume. So the portion of charge enclosed for any radius less than A is going to be only a component of that. So that's going to equal negative the symbol, charge density times 4/3 pi r cubed, because we know that we just figured this out in terms of the density, and this would be the particular radius that's less than A. So we multiply those two together, which is basically the charge density times the volume for any radius less than A. We end up getting something like this, where I don't think I did that very well. Dagnabbit. And I don't think I showed that very well. So we would have to show negative Q over 4/3 pi A cubed times 4/3 pi R cubed. And then that's going to equal that over there would equal E times A, the surface of the sphere, something like that. I think I handled it down here where I figured out how that density relates. So it ends up being QR over 4 pi epsilon sub naught a cubed directed inward because it's a negative charge. That's tough. Like I said, I once thought thing, I think I did above, I actually did it below. So that's the correct answer, but really tough. So you might give up at that point. But now let's take a look here. Between A and B, only negative charge Q is enclosed. And there's no charge here because this is empty space. So the electric field is simply E times A over the charge enclosed over E sub 0. So that's Q over 4 pi r squared E0, or negative KQ over r squared. I just put directed inward or outward, so I didn't put necessarily positive or negative because field has a direction. For this, in this region, even though this outer conductor has a net charge of plus Q, we know there can't be any electric field in between this inner and outer wall of the conductor. So therefore, I'm going to have negative Q on the inner wall, or pardon me, positive Q on the inner wall to compensate for the negative charge in here. So the net electric field in this region between B and C is 0. So that's pretty easy. And then outside of this outer wall, the net charge enclosed is a negative Q here, plus 2Q here, so the net charge enclosed is plus Q. So once again, now we're going to look at Q over 4 pi r squared epsilon sub 0, or you could say KQ over r squared. Now this is directed outward because it's got a net positive charge. So I hope that helps. Again, I think it's something where, hopefully it helps, but it's a little challenging for that first one, a lot challenging for that first one. The last 3 parts of this, though, are not that challenging.